Check for submissions. So is your homework 4. This is to enable your more timely program assignment. Okay, so that now you're not, for a large program assignment, you don't delay everything to the very last week. Okay, so this routine is to get your idea to talk to establish when you do computations, in addition to the precisions from the H and P, okay, the HP adaptivity will be one big thing in the entire semester. There is something that's caused by round of errors. Okay, you have finite precision. Okay, you can improve your computational precision approximation by using smaller h or higher order functions, but they are in the limit of the finite precisions in your machine. Okay, so the expected answer for this, okay, is something you should see that when you calculate your local differentiation, reducing of h originally, okay, by the decreasing h, first order scheme, the error is decreased like your h, selection of h. Okay, just that is should be so. Okay, the second column, I added 10 to the 8th. Okay, this one is at 10 to the 8th. This will pollute the precision, right? Because I force your calculations of the plus 10 to the 8 before you minus something small. Okay, but it's platform dependent. Some platform, especially Python, many times, because it's not designed for efficiency, it does a inline expansion. Okay, it's playing smart. If you do this in an interpretive environment, and if the Python and some C++ as well do inline expansion, he will first perform this line symbolically. That symbolically, these 8 will be cancelled before they do any computation. Okay, this is called inline substitution. Okay, something that's some platform, especially Python, can do this. It's an interpretive language, so it actually has many times do inline expansion before the computation is performed. Okay. And for Python, actually, sometimes it also adjusts the precision. It detects that this one requires higher precision, it automatically switch precision. Okay, some of your Python, you should see that. Very different from your MATLAB or C++, which is strictly double precision implementation. Okay. It seems that Python is better in that handling. Okay. There are 2 caveats. Okay, first, okay, it's change precision in the middle of computation hurt so badly in computation efficiency. Okay, but Python is not meant to let you solve gigantic problems, right? So it's for inline. It's guaranteed I do as good as a job in this. It's an interpretive language in this line, and that is goal. And you achieve the goal, okay? But for something that's gigantic matrix computation, you will find the efficiency is much lower. In your second homework, that where I ask you to print out the CPU time, okay? If you want to try this, you can find it, okay? When you deal with that gigantic matrix, okay? Gigantic matrix, compare the time in Python or in MATLAB, okay, or in C, okay, you will find that the different language optimized for different things, okay. So inline, it's good, but can be expensive. The second more troublesome thing for this kind of inline expansion or change precision when you require it is actually the unpredictable behavior. For a programmer, many times that you have the precision in training. Okay, if there's something automatically adaptive. It may throw you off expectation. Okay, this is more clear in the next example. Okay, next example will be even more clear. It throws you out of your expectation, and many times can create another very difficult to find bugs. Okay, if things are within your expectation, you can write your debugging program, testing program according to your expectation. But if the machine is doing something that's not well documented, okay, many times it's a bug, very difficult to find. Okay, and this is the bug. Many times it's because different machine platform implement the adaptive scheme of Python differently. You thought Python will give you this, but you transfer another platform because it's not a standard feature, then another platform may not work as you expected. The answer is not wrong. Don't get me wrong for the saying that the answer is wrong, but just the answer is not what you expected. Okay, not what you expected is hard to debug. Okay, because you don't know exactly what's going on. Okay, so there are two caveats. Okay, so the thing is here you also see the third column. It's I use a higher order of approximation, so it will improve. Because second order approximation on the quadratic function, it is exact to begin with, right? So you use, these will hit the bottom of precisions, which is about 16 digit, okay? Right at the first iteration, okay? And then you will just get polluted, right? Because anything else, I already hit the rock bottom, right? There's the highest precision I can have. You will increase gradually and increase due to the precision pollution for all the calculation, okay? And you will hit the the error will start increasing instead of decreasing with a smaller h. And higher order method, that will happen earlier, which is also true, right? If you think about it, if I use a more precise method, I will go to the precision limit faster. That means if you really have a smaller h, right, your second order can give more errors if you are not careful, because you hit the rock bottom precision faster. Okay, so this is what it shows you. Again, dependent on your platform, how they handle large number minus large number, give you exception or not. This can be totally error. Okay. The 0 is correct, right? 2 is very wrong. Or because some of the implementations, when they cannot handle the precisions, it tells you and things propagate, become not a number. Okay, so it's not strange. This is the other behavior of calculating the cube, and the focus is on this eta. Okay, so you estimate your answer. You estimate your answer, and you do the different approximation. Okay, this is by h, this is by 2h, this is by the second order scheme. Okay, second order scheme. Okay, so this you can first observe. It's how it proportional to h. Okay, how it decrease. I may have something. This should be 10, not, I know it's 4, okay, the value here is 10. It's a first order scheme, so every time it decreases by 10, sorry. I did it, this is, to me, you should be doing 2 to the minus 4 to 2 to the minus 20, okay? But what I have in this column is 10 to the minus 4 and 10 to the minus 20, okay? I apologize, okay, so my fault, okay? So, but the first thing is that you should decrease, right? Just like the h decreased by 2 times, the precision should be decreased by 2 times, right? And if here is 10 times, so it's decreased by 10 times, okay? Eta, on the other hand, okay, when this is accurate, this should be 2, okay? This is the absolute error because I know the ground truth. This is I don't know the ground truth, just compare these two answers and estimate it, okay? When you are not losing precision, this should be always 2. But when you are losing precision, then become NaN. Okay, this is a check meant for you to see that. And here, I probably give it too small, okay, too large. It should be base 10, okay, base 10, and the things you can go further down so you can see this. Okay, many of your implementations, this is still a 2 all the way down, because 2 to the minus 20, which is nothing but 10 to the minus 6, is still not large enough, okay, not small enough for you to see the degradation in precision. Okay, so again, I didn't grade your things, it's just force you to perform these calculations, and you can, and this at the end, right, what you have is these are routines together with your program assignment 1 that you can take with you, right, to execute and know the behavior of your platform. The calculation is dumb, okay, it's so simple, okay, but it is a good demonstration of how your platform handle the precision and whether it is expected in the way, say, the first order decrease as first order, second order decrease as second order, and when it is hit the bottom of your limitation of precisions, what happens? How your platform handles, okay? So these are things that I think part of the utility you should take with you to, if you start a program in a new platform, something you should run and you should know. Okay, you should know the behavior of your platform. Okay. So this is your homework 2. Homework 4. This one thing I want to get clear. Page width. Okay. So when you do these operations, these 3 operations on this matrix, I want the full matrix and the row compressed format, okay, because they are just different in data structure. It should be, all the operation should be element by element exact. Okay, you may feel silly, but this is an important thing in proving that your implementation is correct. Okay, this is a little bit silly, okay, but the purpose for you to compare element by element, because the only thing I change is the data representation. I even didn't change the precision, right? The precision should be exactly the same, okay? But when you deal with a sparse matrix, right, something that's indexing, how do you know it's correct? How do you know your operation is correct? Wilkinson principle, implement 2 times by 2 different data structures. If they're element by element correct, likely you have done the implementation correctly. Okay, so this is the purpose. Okay, you along the way you feel a little bit silly, then what am I doing? Things, it's give you an example of debugging. Okay, and you should is also give you an input about modular programming. The modular programming should be to the extent that each module have its own regression testing. Okay, the module need to be encapsulated in the way that that module can be tested. And I know the implementation is correct, so that it can be not only used by other programs, but reliably used by other programs. Okay, it's not just for your programming ease, right? Any module, when you do modular programming, one of the main things is that module can be verified by itself. Okay, so this is, and then this large matrix for sure. This is from SPICE. If you have run SPICE before, this is from SPICE. So this can only be done in sparse format. Okay, again, the operation it's for debugging purposes, okay? The operation doesn't mean anything by itself, okay? But it's for debugging purposes, and this is to encourage you to, but debugging, many times when you write larger programs, you have to automate it. You cannot look into your source code and do debug, because the source code grow, there's no way you can go into the program and then know that there's no problem. So you invent some fictitious operations to become a number, you compare a number. and make an automatic report in your debugging. Okay, so this again, it's a realistic data set, okay, and tell you another possible debugging method. Okay, so change your mind. You say, what am I doing here? Okay, isn't I don't get the point of the assignment? The assignment is to show you how you should write your regression testing in the long run. Okay, not for the computation itself. Okay, the computation itself is silly. It's supposed to be silly because silly, you know exactly what happened. Exactly know what happened, you can debug it. Okay? And you can debug it, you can give you an automatic report whether what you implement is correct. Okay. Any question on this? Okay. Yes, you don't have. For the first one or homework 4? Okay. Yes. First part?
Yeah. So when you say the full minus the sparse, do you mean that when we should assign the full matrix by ourselves and then the sparse should be after we get the full matrix from the whole?
No, you implement that matrix 2 times. 2 times, 2 data structure.
Yes.
Duplication. Duplication is 101 in testing. Okay. So A, your full matrix, you declare an Aij, right? A55. Okay, and that you input that matrix, right? Line by element by element. And then you do the row compressed format. This is 6, column index. This is 12, 10. 12. Number of nonlinear element, value, 12, within a structure or object that's your sparse element. Okay? You implement this exactly for the 3 method, the permutation, the product rule, and things. Give method for this data structure. Give method for this data structure. In your main program, call the 2 things exactly, right? And the result should be element by element exact. Okay? You create a data structure. You create a method to access the full matrix, right? That's one. You create this redundant data structure for the sparse matrix, and you create the method permutation ax equal to b, ax a times x. Okay? You perform the same operation. The only difference between these 2 is the data structure. So the result that come up with should be element by element exact. And you use that to check whether your implementation is correct. Okay. Redundancy, right? It's, if you want to be philosophical, okay? Anything you want to check, redundancy, right? If I don't know the true answer, how can you check anything? Redundancy, right? Implement it twice, implement 2 methods, 2 data structures, 2 algorithms, 2 methods. You do it redundantly and you check the consistency. And that is the Wilkinson principle.
Okay, so we should have like the 3 methods for
3 what?
So we should have the 3 methods, that's the row permute and the other 2 for
Yes, yeah. For both.
Matrix, row storage, and then for part 2 coordinate storage, we should have like a different set of methods for coordinate storage.
A same method, but operate on different structures. Same method. This the method, the 3 methods you need to implement, but on 2 different data structures though. It's like doing your
like 2 methods with the same name but operating in different ways.
That's to you. Okay, you want to practice the namespace. Okay, you want to create a namespace that use exactly the same name. That's your choice. Okay, but for sure, in any function, you cannot create the function with exactly the same name without association because the compiler will kick you out. Okay, you can in the MATLAB way, this will be you add a header for row permute. Fine. Okay, or in the C++, namespace way, it will be something like this, right? It will be 4 and 4 row permute. Use the namespace way to deal with it. But for sure, this function is implemented twice, right? One on the full data structure, the other on the sparse data structure.
And then another one for the part 2, that's coordinate storage.
There's only 2. One for full, one for row compressed sparse storage.
No, in part 2, where we...
In part 2, this is not possible, right? So only row compress is required.
But the matrix in part 2 is in coordinate storage format.
Yeah.
So do we have...
You have to write something to construct your row compress things, right? Row compress format. You build your element, right? So you build element, and you read the file, right? Read the file, and then do your pointer.
Yeah, so
things.
my question is, are we, like, the coordinate storage, are we supposed to convert it to a compressed row storage format? Or we should write a different function, but with the same name that works, like, for example, row...
I don't want your coordinate storage. I want your sparse matrix only in row compressed format. The matrix is given to you in the coordinate representation. Yes, okay? But you can convert it. Okay? You will very soon find that row compressed format or column compressed format, it can be executed, okay, in normal operations much more convenient than the unsorted coordinate storage. Once you implement it, this row pointer actually very convenient. Okay, so this second part, I only want the row compressed format. Okay, the matrix MART, this gigantic matrix given for your testing, is in coordinate storage because it doesn't want to assume that what is you will handle, right? So it's a public Excel sheet-like forms, but you parsed it to become your own data structure, which is very common for handling large data, right? When you post the data, you want to do a data format that's as generic that can be Excel or Microsoft compatible, okay? But when in your own data storage, you want it to be the most efficient and convenient one for your purpose, right? So parsing the public data to translate into your desired data structure, this is something that's commonly done, okay? So if you have such an efficient data structure, don't post it if this is for everybody to use, okay? But post it in the most generic format, okay? Not optimized for any efficiency because you don't know what other people will want to use it. Again, here's a good example, right? This National Institute of Standards, right? They think that the linear algebra is such a universal interest in any field. So they posted this test matrix for you to play with. Okay, so when they post it, they use the most generic format as a coordinate storage. Okay, they cannot use the full storage for sure because this cannot be handled by most computers. You can try, okay? Try this one, declare this is A, 10 to the 6 and 10 to the 6. Your computer should kill you in the first step. Okay, if it doesn't kill you and try very hard to do it, that's a crime, okay? If the computer or the interpreter or the compiler doesn't even have an idea about what they are dealing with, okay, I declare something that's terabytes, no, it should kick you out, okay, directly. So full matrix even for the circuit, the matrix I posted is actually considered rather small. Okay, it's a simulation of, let me tell you what it is, a page of memory. A memory circuit that's contained a page. That's all. That's you know, your computer typically have about 1,000 pages for the DRAM, and about 100,000 for your solid state disk. That's how small the circuit is, okay? But it generates, because each element nodal voltage will generate an entry in the matrix, so it becomes that matrix I posted. It's not a large circuit actually, okay? Any question?
Can
Yes.
you scroll down?
Yes, scroll down here. Part 2?
Yeah, part 1.
Part 2? Okay.
Part 1.
Part 1, okay. Yes.
So here there are
Three operations.
So we perform it on full matrix and then on row compressed matrix.
Yes.
And then check element by element wise whether the result is the same.
Yes.
But what is the second part, like summation of xi of full? There's no x of sparse, right? Only A is
Sparse.
sparse.
Yeah.
So the x part is actually
X is the same.
not.
There's no sparse format for factors, because anything, even the sparse matrix, work on a factor, the factor will be filled up entirely. And so, but the matrix is n square storage. Factor is n, right? So there's no need for factor to be usually to be in sparse, okay? There are questions that even when the vector need to be sparse, okay, very few, okay? Then there are very little thing you can do about that problem. If you have a correlation matrix, okay, that's of rank n, but you have even problem in store n, or the factor, okay, then it's usually problematic. There are methods though. Okay, there are, especially in astrophysics, okay, there are things, it's just that even one factor is so huge, you have to use the sparse format, okay, and the correlations and all these things, they are, that's off the topic we discuss here, okay. If you're interested in it, I actually have written those programs, okay. It's called the matrix list solvers, okay, but that's way beyond our scope. It is possible, okay. Vector becomes sparse, I make the computations, okay, matrix lists. Possible, but it's off the topic here.
And output should be written to file or just
Output do a whatever norm of element by element. They need to be exact, right? Because the only thing you do here, independent of the precision of your computer, right? It's exactly the same operation. The only difference is the different sequence in the way you access the data. You want to make sure that the sparse element is accessed correctly. Okay? So it should be your element by element should be exact on any platform, different from your previous assignment. Should be exact, okay? There's no error here on your own platform, because it's the exact same operation, but just implemented by two set of programs. So you should check element by element. It should be exact, okay? There's no precision problem here, not like your previous assignment.
No, I meant like first we do the permutation on a full matrix and print the result, and then do it.
You don't have just do this all, finish and then compare, right? Finish the three operation and compare the final result to be element by element exact, right? That's again another principle of testing. You want something, you have to scale, right? If you have so many detailed information to report, that also means when you want to know the answer is right or wrong, you need to spend a lot of time looking at it, whether it's right or wrong. You want to automate, right? So this automate to the degree, right? I calculate element by element, what's the difference? If the result is 0, I pass. If the result is not 0, then there's a problem. Okay, you can go back and check, okay? Then there's a detailed report for you to do. But there's always an easy yes or no answer for you to check whether this module on this platform is verified. You want to be an automated check instead of a detailed check. Detailed check should be available when the automated response is no, something is wrong. Then you go to debug, right? But there always has to be a way of an easy check. It just report, verified or not verified. Yes, maybe.
The data in this matplots.mtx is stored in, so first row is, so the first column is row and the second is column?
Yes. It's just a matrix, so if that actually doesn't matter. but yes, yes.
One more thing is,
And you can check the matrix, right? Because a sparse matrix, they give this building plot, right? You will see, right? The second row is almost filled. There's a diagonal and there's a column that's going like this. You can roughly know that the sparse structure. For sure, this is from 0 to about 10 to the 5th, right? It's a large matrix.
and that function of permute accepts a matrix and a vector. Do we have to write from vector as well, or just matrix?
Just matrix, because there's no ax equal to b here, right? So only a. There's no b.
So no need of passing a vector.
You can pass a 0 to it. This is meant to be used in later, so please write a b correspondingly. Okay, but you can give O0, right? Because it doesn't matter for this assignment. But this assignment is meant for you to use the sparse structure you created to do something meaningful, and the part of the 3 method has already been verified in part 1 that is correct. Okay? And in part 2 is correct in this very large storage matrix. Okay? So I'm going to give you, in the assignment, give you a real problem to solve using the verified routines. Okay? Again, this is 101 in any robust computing, right? When you plan something, right, you write modules. The smaller modules is testable by itself. You go progressively to larger and larger problem, right? But each of your basic functions need its own test functions. Without that, you finish writing a big program and then you think about how should I debug. It's way too late, okay? Way too late, okay? And this, yeah. Even the most horrible thing is that when you write a big program and there's no good way to tell that it works or not, you say, oh, it worked. For my one test case, it worked. Great, okay? That's not good, okay? And unfortunately, that's how of the, it's recorded, so okay, I'll still say it. Unfortunately, there are many products on the market doing that, okay? They don't test it, they don't verify it, okay? Annoying, right? And it's buggy to the degree there's no way you can debug. And there's no way to use it, okay? First thing, this is the first annoying thing. The second more annoying thing is there is a bug list and they don't fix it, okay? It's just annoying, okay? It's just that, but you know, but for sure, in software engineering, there are all these different principles about version, how to maximize your cells in each version and things. That's not in the discussions of writing a robust program. Okay, your manager may ask you something, say, okay, there is a bug list. I know, don't fix it. Okay, it's totally possible, okay? This is, okay, I'll name him. I like Bill Gates now, so I think. In Bill Gates, in one of the Windows 7 announcement, he said, yeah, we know there's about 2,000 bugs. Right? And there's 2,000 bugs. And the computer, during the demonstration, crashed right then and there. He said, oh yeah, we have 2,000 bugs. Right? And the reason why it doesn't fix it, because it's a sales issue, right? How long you want the previous version to sustain, how much you want to predict the people pay for the new version. So even the bug is entirely due to the modular testing. Your manager may ask you, okay, for this release version, don't fix it. Okay, that's possible, okay? But that is beyond, again, the scope of this class, okay? And there are, the things, first learn this, okay? For when you go to your real job market, there will be things more complicated than this. There will be legal issues, okay? Legal issues about how you actually copy some other's program, but you want to avoid people suing you. So your manager asks you to do something different on the software. Possible, okay? Reverse can be possible. You write a program, everything works, everything tested, and you know that there's no way you can keep this to yourself. You will leak somehow, okay? So you watermark your source code to make it totally unreadable. That's surely possible, okay? But those are beyond the discussion here, okay? So in the real world, there are more, when there's more scientific and engineering interest to pursue the truth, when you try to pursue the profit, it can be more complicated, okay? So there are other techniques I'm not teaching you here, but just let's first learn this, okay? At least you know how to pursue the truth, okay? And then maybe later you have other goals for your profit, for watermark, for something, then let's learn that, okay? But at least to yourself, you know how to write a reliable program, how to test it and verify it, okay? Later on, let's figure out something else that's the best profit for your product, okay? That's another thing, okay? Yeah, thanks for the discussions. Okay, so immediately, actually, in this one, we have a practice, okay? So this is the other things. There are two things that can pollute the accuracy of your solution of a linear algebra or a linear systems, okay? I just finished one of the faculty interview, our new faculty interview, and then during the dinner, he's telling me, we asked the question, do you really belong to computer science or belong to electrical engineering or ORIE or even business school? Because interviewing in all the different departments. The guys sit back and say, I'm just doing linear algebra. To say in that linear algebra is that broad, okay? He does research on linear algebra, so all the electrical engineering looking at him for information theory issues, computer science is looking at him, business school is looking at him. So, but what I'm doing is just linear algebra is that, as I stated in the thing, okay, is all the problem. Maybe after linearization, we're doing this, okay? So here, let's an example of saying the matrix conditioning. This will show one of the sources that the linear algebra does not give you the correct results, okay? I'll give you two more examples that don't give you the correct results. This is because yield conditioning, okay? The coming one in the Thursday, tomorrow night, I'm going to tell you what is called pivoting. That can, if you run pivot, can pollute your solution, okay? I'll tell you how this happens. But this is just because of yield conditioning, okay? Yield conditioning, okay? And you can calculate this, okay? Perturb this one a little bit, you'll get a totally different answer. And the reason is simple, and you can practice very quick. The other is like you perturb this Jordan block, okay? Perturb it a little, okay? The solution actually change significantly. It does happen, okay? It does happen. So let's show you the conditioning, okay? Implement this, okay? This should be 5 seconds, 5 minutes, not 5 seconds, sorry. 5 minute things, okay? The idea is the first row and the second row, if the E is 0, is degenerate, right? So it will become solution of a 2 by 2 matrix exists, right? When the matrix is not degenerate. Right? It's the cross sections of two lines. When the two lines have the same slope, either it's parallel or it has infinite solution, right? So when E go to 0, then the matrix become degenerate. Okay, let's test the E. Okay, get a minus E, and then okay, when you solve, however you solved it, okay, 2 by 2 matrix, you can do very easy solution to that. Okay. 2 by 2 matrix, you solved it, okay? Test on the residual factor. How good is your solution? Okay? So you should expect that when E start decreasing, this one become more and more horrible. Okay? And this is because the pollution from the matrix conditioning, right? Matrix conditioning as that, okay? So let's implement this and see the behavior. 2 by 2 matrix can be solved in just you subtract the correct amount of first row to second row, making the eliminate the x1 dependence in the second row, and x2 is out, substitute back to your x1. Okay, if you haven't done that. No, give me the residual factor. So if you solve it correctly, it should be 0.
It's 0 for all except like 2 values.
2 values at the end.
Yes.
How large is the residual factor become?
Like, this is the present. Oh, this is just 1e minus 7 range.
Okay, so it's not very large. Okay, so you can. Okay, so the double precision in MATLAB, I believe, is that MATLAB? MATLAB. Okay, so to here, it's you have precision all the way to 10 to the minus 8, which is pretty good. Okay, that is actually expected, right? 10 to the minus 7 or 10 to the minus 8 is where the precision is gone. Right? You have double precision, 16 digit, right? 16 digit. So in here, for here that the towards the end, the precision will be lost. Okay, feel free to go down. Okay, in your loop, go down this to 10 to the minus 16. You will probably see the behavior even more clearly. Okay, but many times the precision start getting lost in the 10 to the minus 8. Okay, half of your maximum precision. Okay. I've been thinking about, now the hacker practice to spice it up. I think you get the experience. Maybe later on I should have a time competition. Okay, but not immediately. Okay, but later on, let's just for fun. I won't use it for grade. Okay, time competition is at least for this level. I think it will be good for your interview or when you go into a hacking competition. Okay, so there actually, let me look it up whether you can have a team to go to Hacking New York. That'll be fun, right? There is a annual competition of Hacking New York. Okay. Okay. So 1 minute left, so I won't go for the next lecture. Okay. So the next one. Just as now you know one error coming from the conditioning of the matrix, right? The conditioning is coming from your determinant or the matrix is nearly degenerate. When you have a nearly degenerate matrix, indicated by how small is the determinant of the matrix, okay, that will pollute your answer. Okay, so one thing, okay. Next coming is something called the steps called the areal decompositions, and I'll show you how in the regular solution of a large matrix, how you decompose your matrix to the lower triangular and upper triangular matrix. Okay, how to do that, and there are two objectives. Okay, first, because it's a huge matrix, you want to do the minimal fill-in. It's a sparse matrix, you will remain a sparse matrix. Goal number 1. Goal number 2, you shouldn't change the answer during the process because of loss of precision. Okay, that's called pivoting. Okay, so I'll introduce to you in this one is how you can do the areal decompositions, which is nothing but the matrix representations of what you do from grade 7. The Gaussian elimination. Okay, from grade 7, you're given the linear systems using the first row to cancel some of the second row and third row, and use the second row to cancel the third row. That's what you did is exactly areal decomposition. There's a one-to-one mapping to the matrix form. I'll show you that, and I show you what's the effect of that fill-in. If you have a sparse matrix, if you're not careful, then you may have originally sparse matrix become a full matrix. Okay. not so sparse anymore. Okay, so how do you deal with the fillings? The second goal, within that process, I cannot pollute my answer. Okay, so these are two things I'm going to introduce to you. For sure, before I say that, a matrix that's by nature degenerate, there's no salvation out of it, right? I mean, it's nearly degenerate. It's supposed to give you a chaotic answer. Okay, so this is not the problem we have just solved. Okay, this is assuming that the matrix is solvable, have a well-defined solutions, but what you should do to pay the minimal effort to solve it, minimal filling, and also on the way, don't pollute it. Okay, so that will come tomorrow night, where I will introduce that to you and give you good pieces. Okay, yes.
What will be the makeup lecture and what will be the...
It's tomorrow night, 7:30 at Philips 228. There's a Blackboard announcement. I hope that is correct. Okay. So there's a, if you forget, just check the Blackboard announcement. There's a makeup class, time and place.